Hello students, today we shall go ahead with the next session and this is going to be a continuation in states of matter itself. In today's class, we are going to study regarding Miller indices, X-ray diffraction of crystals and Bragg's law. In today's class, we are going to study regarding Miller indices, X-ray diffraction of crystals, Bragg's law. Coming to Miller indices. Miller indices are symbolic vector representation for the orientation of an atomic plane in a crystal lattice and are defined as the reciprocals of fractional intercepts which the plane makes with the crystallographic axis. Miller indices are a symbolic vector representation for the orientation of an atomic plane in crystal lattice, and they are defined as the reciprocals of the fractional intercept which the plane makes with the crystallographic axis. So the rules for determining the Miller indices. So we are going to determine, first is determine the intercepts of the phase along the crystallographic axis in terms of unit cell dimensions. So first we are going to determine the intercept which is going to make with the axis. First step is going to be we are going to determine the intercepts of the phase which it makes with the axis. Then we are going to take the reciprocal of it. Then we are going to clear the fractions. The reciprocals, after taking the reciprocals, I am going to clear the fractions by multiplying it with a suitable integer. Then it is reduced to the lowest terms. For example, let us consider one example. Here, this is going to be a unit cell and it makes an intercept. It makes an intercept along the x-axis, that is along A is going to be 1 unit, along C is going to be 1 unit, and along Z is going to be 1 unit. So the intercept length is going along A1, B1, C1. And when I take the reciprocal of this, it is going to be 1 by 1, 1 by 1. And if I have to clear the fraction, I have to multiply it with a suitable integer. So because all this is 1, the Miller indices is going to be 1, 1, 1 itself. Let us go on to consider another example. Here, if we are going to see the intercept made by this unit cell is going to be along A is going to be 1 unit, along C is going to be 1 unit, but along B there is going to be no, and it can be taken to be as infinity. So in this case the intercept length can be taken as 1 along this axis, that is A, it is going to be 1 unit, and along B it is going to be infinity, and along C it is going to be 1 unit. So next what am I going to do is I am going to take the reciprocal of it. Then I am going to clear the fraction. Once I clear the fraction, this will be 1, this is going to be 0, and this is going to be 1. So in this case, the Miller indices is going to be 1, 0, 1. In this case, it is going to be 1, 0 and 1. So like this, we are going to determine the Miller indices. So if we are just before going to X-ray diffraction of crystal, let us know what are constructive and destructive interference of wave. So this is going to be when two waves are going to approach. What happens is here, if it is going to be a constructive interference, this is going to be in phase. We are going to get the final one like this. That is, it is going to vibrate along this direction. But if it is going to be a destructive one, it is going to be a destructive one. This is going to be the propagation of wave. This is going to be the amplitude over here. And then if it is going to be a destructive one, what happens is this is how we are going to get the final one, and this is going to be out of phase. So this is about what are destructive and constructive interference. Coming to X-ray diffraction of crystals. The electrons oscillate under the influence of the incoming X-rays and become secondary sources of electromagnetic radiation. The electrons are going to oscillate under the influence of the incoming X-rays and become secondary sources of electromagnetic radiation. The secondary radiation is in all the directions. The secondary radiation is going to be in all the directions. The waves emitted by the electrons have the same frequency as the incoming rays. They are going to be coherent. The waves emitted by the electrons have the same frequency as the incoming X-rays. They are coherent. The emission can undergo, electromagnetic radiation can undergo constructive or destructive interference. So, this is going to be the incoming X-rays and the emitted one is going to move in all the directions. And the oscillating one is going to be in plane with the incoming rays. So, this is how we are going to show the schematic one of the emitted electromagnetic radiations when they are going to fall on the particle, when X-rays are allowed to fall on the particle. Coming to a brief derivation of the Bragg's law, let us consider two X-rays are going to fall on a crystal. And if it is going to be a constructive interference, it is going to be X-ray, this one is going to get deflected over here. The X-ray 2 is going to go to the next plane and gets deflected. The distance between the two planes over here is going to be D. The second one is going to cover an extra distance of AB and BC. It is going to cover an extra distance over here. So now it is going to be this one, n lambda will be equal to AB plus BC. N lambda will be equal to AB plus BC. Then I know here AB will be equal to BC. AB will be equal to BC. So if AB is equal to BC, then n lambda will be equal to 2AB. But what do I know? If this is going to be theta, then sine theta is going to be, this is going to be the opposite side by hypotenuse, and that is sine theta. So it is going to be AB by D. So AB will be equal to D sine theta, or n lambda is equal to 2D sine theta. This is going to be, sine theta is going to be opposite here. This is going to be by this distance. So, n lambda will be equal to 2D sine theta, or the wavelength will be equal to 2D here. The wavelength will be 2D HKL. This is going to be the Miller indices sine theta HKL. Bragg's law. In Bragg's law, what did we do? What are we going to do is we are going to consider crystals are made up of parallel planes of atoms. These crystals, this is going to be the crystals. Crystals are made up of parallel plane of atoms. The incident waves are reflected specularly from the parallel planes of the atom. These are the incident ray, that is, if I go on to consider AC is going to be the incident ray which is going to get reflected along this plane, and BE is going to be another one which is going to get reflected here. So with each planes reflecting only small fraction of the radiation, like lightly silvered mirror. In mirror-like reflection, the angle of incidence here, like mirror reflection, if we are going to consider, the angle of reflection will be equal to the angle of incidence is going to be equal to the angle of reflection. That is, this angle of this is going to be the angle of incidence will be equal to the angle of reflection. So the incidence, if the incidence angle is going to be theta, then even the reflected angle is going to be theta. X-ray wavelength is going to be lambda. Then the total diffracted angle is going to be 2 theta. If the length, this is going to be the length, D will be the same as that of EF. the length DE will be equal to same of EF. So that the distance traveled by the bottom wave is expressed as, the distance traveled by the bottom wave is going to be expressed as EF will be this one. EF will be equal to d sin theta. Similarly, even DE also will be equal to d sin theta. This is going to be the distance traveled further. So it will be d plus EF will be equal to 2d sin theta, or n lambda will be equal to 2d sin theta. This is going to be Bragg's law. So what did we observe is, in case of a constructive interference of radiation, for successive planes occur, then the path difference is an integral number of the wavelength. So what do we observe in Bragg's law is, if there is going to be constructive interference of the radiation from successive planes, then the path difference is going to be an integral number of wavelengths. That is, n lambda will be equal to 2d sin theta, and this is called as Bragg's law. Here d is the spacing of the planes, n is going to be the order of diffraction. Because sin theta will be less than or equal to 1, Bragg reflection can occur only for wavelength satisfying n will be less than or equal to 2d. Bragg's reflection can occur only when the wavelength is going to satisfy n will be less than 2d. This is why visible light can't be used. That is the reason why we cannot use visible light and we are using X-rays. No diffraction occur when this condition is not satisfied. The diffracted beams, reflections from any set of lattice plane can occur only at a particular angles predicted by Bragg's law. That is, the diffracted beams, when I tell diffracted beams, it is going to be the reflections from any set of lattice planes can occur only at a particular angles predicted by Bragg's law. That is, 2d sin theta is equal to n lambda. Okay students, in today's class we have studied what is Miller indices, what is X-ray diffraction of a crystal, and Bragg's law. The derivation of Bragg's law in a very brief way, and why Bragg's law cannot be used in case of visible light and we require X-ray only because it is going to it has to satisfy the required condition.